Okay, so today so continuing our digression from the coloring. So we are defining the product of two graphs. There are several notions of graph products. So here we define, first the Cartesian product of graphs. So given graph H and G, so we define the Cartesian product of G and H, denoted by G, this box symbol H. On the vertex set, which is obtained as the Cartesian product of the vertex set of G and vertex set of H. So it's basically the ordered tuples, where the first element comes from the vertex set of G and the second one comes from the vertex set of H. So on this vertex set, two vertices are adjacent. So let's say GH is one vertex and G dash H dash is another vertex, and they are adjacent if and only if either G is equal to G dash, right? And HS dash belong to the edge set of H. So HS dash is an edge in H and G is G dash. Then in this case, we have an edge between these two pairs. Or H is equal to H dash and G dash belong to edge set of G. So this is the definition of the graph, Cartesian product of two graphs. So just to see this, if you take just two edges, let's say AB is the edge in the first graph and 1, 2 is the edge in the second graph, right? So AB is an edge and 1, 2 is another edge, then the product of these two edges is precisely this C4. So you have A1, A2, B1, B2 are the vertices of the new product graph, and A1 is adjacent to A2 because the first component is the same and 1, 2 is an edge in the second graph, and similarly the other edges. Now, so once you know what happens for a pair of edges, you know essentially what happens in the entire graph. So that is why this notation for the product is also the box symbol, which is the four-cycle. On the other hand, this product name in the literature is like very highly confusing, because if you look at 10 different papers, you can end up seeing 10 different names for the same product. So sometimes people call Cartesian product as like some other products like tensor product or like product on many other names you will see. But for the time being, we will just stick with Cartesian product. But anytime you are discussing or reading some paper related to one of these products, you should see what they define as the product. So because just don't look at the name. But for our course, Cartesian product is only this. Okay, now another example is the the product between this triangle and the tree on the right side, and you can see basically what happens. So another way to look at this is that this product is that you replace every vertex of let us say H with a copy of G, right? So if you look at this product, you see that every vertex, vertex 1 is replaced with this copy. You can see here. Somehow it's not working. Anyway, so you can see this copy is corresponding to the vertex 1. Then you have the next copy corresponding to the vertex 2, etc. Right? So you basically replace every vertex of H with a copy of G, and then the corresponding vertices. So if there is an edge between vertex I and vertex J, then you take the corresponding copies and then put a matching between the corresponding vertices. And basically, like, you put a perfect matching between the vertices of these two graphs if there is an edge. So basically, you have each corresponding vertices will be joined by an edge. So this is how the structure of the graph looks like. And one can see that this is also equivalently you replace every vertex of G with a copy of H and then do the same thing. You put an edge, a matching between the corresponding vertices if there is an edge in the graph G. So and one can see that this is actually a symmetric product. So I will leave it to you to prove that the product is symmetric by taking this. Only the the labels of the vertices will be different, but they are isomorphic. G, Cartesian product H is isomorphic to H Cartesian product G. You can try to prove this by giving an argument. Here is another example. You have the product of three graphs. So you have the first graph, both all three are edges. So if you take the product of these three, you will get what is called this cube graph. So now you can see that basically the hypercube graph that we defined a long time back is precisely obtained as the Cartesian product of just edges. So you take k edges, their Cartesian product is the kth hypercube, right? The hypercube of dimension k. And if you take two paths and their product, it will look like a grid, and it's called a grid graph. And you can take more paths, and you will get higher dimensional grids, and it has some nice properties, structures. Then maybe not at this time, but one can try to prove that this Cartesian product, has a unique factorization theorem. So you can define what are called prime graphs, etc. And all. I don't know whether we will cover it in the course or not, but I will at least try to give it as an exercise to you, or with some some hints on the way. We will see, but not at the moment. Okay, what I want you to do is to look at this product of several graphs, try with several of these examples, and come up with some properties that you can come along with, like in terms of the graphs, components of the or the factors. I want you to come up with the parameters, some simple parameters of the product graph. Think about that. We will come with a list of these questions also, hopefully in the next slides or something. Then another notion of the product is called the direct product or tensor product. Again, you will see these names being used in the other context and this context, etc. Because for example, this is also defined on the the product of the the Cartesian product of the vertex sets. So therefore, some people call this as also as the Cartesian product. But of course, for us, it is the previous definition. Okay, so what is the direct product? So if G and H are two graphs, the direct product of G and H is defined as follows: that you have the vertices GH and G dash H dash adjacent if and only if G dash is an edge in G and H dash is an edge in H. So we want both these edges to be present to have this edge between the pairs. So this will tell you, how the graph is going to look like if you have AB is an edge and 1, 2 is another edge. The product of these two, the direct product of these two, is precisely going to look like this. That you have A1 and B2 because AB is an edge and 1, 2 is an edge. And B1, A2 because AB is an edge in G and 1, 2 is an edge in. So we have these two edges, and therefore the notation that we use also looks similar to that. Just to remind you what is the product that we are talking about. Okay, so for any two edges, and therefore for the entire graph, so we have the product of this triangle and this path is going to look like this. You can just verify it, right? All the pairs of edges you can verify because AB is here, 1, 2 is here, therefore you have A1, A2 to B1, right? And similarly A1 to B2. right? So similarly, you can verify for other edges and verify, see it for yourself. So here are some questions to think about. So we are actually looking at the chromatic numbers of graph. So can you find out some bounds for the chromatic number of the join of graph in terms of the parameters, some parameters of G and H, like in terms of the chromatic numbers and some other parameters maybe. Then what about the chromatic number of the Cartesian product? Again, in terms of some parameters of G and H. If possible, of course, in terms of chromatic numbers of G and H. And you want to include some other parameter, it's okay. At least find some bounds, or if you can find some, equality, that is the best, right? You can precisely define it in terms of the parameters, it will be better. And similarly, find some bounds for the direct product of G and H in terms of the parameters of G and H. Okay, so look at these three questions. Try to work out, some examples and see, and then come up with some idea like how it, what relation you can see, and then try to come up with this as a result, and try to show it. Then some few other questions to think about is that what you can say about the maximum degree of the join or the Cartesian product or the direct product in terms of some parameters of G and H. And again, what I mentioned, you can try to prove it. The join of G and H is it isomorphic to join of H and G. Similarly, the Cartesian product and direct product are they symmetric. Okay, some questions and so we were looking at this graph coloring question. So and then coming back to graph coloring, one can ask, okay, given a graph, how do you go about finding a coloring, right? So there are graphs where one can show that to find the exact chromatic number is very 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 difficult. I mentioned this, right? So one can show it is NP hard, and therefore it's unreasonably hard. Now, but suppose you want to say that, okay, I want to come up with at least at the first step I want to come up with some proper coloring of the graph. So how do you go about doing this? So one method that one can always think about is what is called the greedy approach. It may not give the best result, but it will give you some result. Right? So what is the greedy? In greedy, you basically pick up some vertex and color it with the. So you are going to use the colors, let's say 1, 2, 3, etc. And I want to use as few as possible. So what I can do is to just pick up some vertex and color it with color 1. Then pick another vertex, any vertex, right? And then see if I can use color 1 on that also, right? Because if that vertex is not adjacent to this, I can still use color 1 on. So I pick another vertex and then give it also the least color that is available to it, right? So when I'm going to color a new vertex, I look at what are the colors that is appearing on the neighborhood of this vertex, which are already colored, right? So look at the vertex, look at the different neighborhoods. Some of them are not even picked up, but those which are we have picked up before, we would have colored it, right? So look at the colors appearing on that set, and then so maybe you have used colors 1, 2, 3 up to let's say 10, right? So far, right? We have colored up to use colors up to 10, but on the on the vertex VI that I am going to pick up, maybe I have used colors let's say 1, 2, 7, 8, and 5, right? So maybe only these 5 colors are appearing in the neighborhood. Then which color I should try to give it? Of course, I can try to give it any color, but out of this 10, but maybe I will go about with choosing the least number which is available to me, right? So 1, 2, 5, 7, and 10, or whatever 8 are used. So 3 is available. So I will color this vertex with color 3. I mean, this is just to decide which to give. So now This way, then I pick the next vertex and see what is the best I can pick. So always give the least index color that is available to us. And if none of the colors that we have used so far is available to a vertex, we have to introduce a new color. So this is the so-called greedy approach. Okay. So basically, you order the vertices in some order, whatever order that you want, x1, x2, etc., xn. Then you color in that particular order. That first choose x1 and then color it with some color 1, and then when I go to xi, color it with the smallest possible color that can be given, and if it is like so all of the colors that we have used so far is in the neighborhood, then we introduce the new color and then continue. And then once you finish with all the vertices, output the coloring and the number of colors that we have used. So this will tell you the chromatic number and also give you a coloring of the graph. Okay. So this is the like very naive approach. It's called greedy coloring. So what are the advantages of greedy coloring and what are the disadvantages? So the immediate advantage is that it is very fast, right? You pick a vertex, just look at the neighbor, color it, and then you can finish off things very fast. And it always produces a proper coloring, right? Because we make sure that when I choose a vertex, it is not given any of the colors that is used in the neighborhood. So therefore, it always produces a proper coloring, and it is very fast. So this is the one biggest advantage that we have. But the problem is that it often uses much more colors than what is the best possible. Even uh, it could be very different from the the actual chromatic number. It could be very large. Now another issue with greedy is that it the output depends on the order of the vertices in which we choose. So can you think of why it depends on the order? To help you with this, I have given a graph here, right? A bipartite graph, in fact. So we know that we can actually color with just two colors. You just choose the independent set, color all with one, then the next one, and color it all with two. You will end up in a coloring with just two colors, right? But now, if I don't choose the order of the vertices, in a proper manner, then I may end up in using many more colors. So the greedy depends on the order of the vertex. So why is that? So let us look at this example and see. Suppose I am going to choose the vertices in the following order, right? So I choose, let's say, x1, right? The order is x1. Then I choose this as x2, right? Then x3, x4, x5, 6, 7, and x8. Okay. So I have chosen this order, right? Because when the graph is given to me, not it may not be in this form, right? It may be just set of vertices, it's neighbored. So I don't know whether the graph is bipartite, what is the order, what are the independent sets. I don't know anything, right? I just know the neighborhood by the computer is given some basically the adjacency matrix or something, right? Or adjacency list. Now, so I pick some random order, let's say, and then what will happen if I choose this order to color, right? So the greedy, what does the greedy do? It chooses the vertex x1 and gives the color 1. Right? Then it chooses vertex x2 and see that okay, x1 and x2 are not adjacent. Right? So therefore, I will give the color 1 here. Now it will choose color, the vertex x3. But now if I choose x3, x3 is adjacent to x2. So therefore I cannot use color 1. So I will use color 2 here. Then I will choose x4. And x4 is again adjacent to x1. So therefore I cannot give 1. But it is not adjacent to x3. So I will color with 2. Right. So the pre-colored vertices. But now when I choose x5, x5 is adjacent to both x2 and x4, which are colored 1 and 2. So I cannot give 1 or 2 here. So I have to use color 3. Similarly here, then I have to use color 4 here and 4 here. So instead of 2 colors, I ended up using 4 colors. But if the order was different, for example, if I was using let's say y1, y2, y3, y4, right? Then y5, y6, y7, y8. In this order, if I was coloring, I would have used only 2 colors, right? y1, y2, y3, y4, I will give color 1. And then y5, y6, y7, y8, I will give color. So therefore, the greedy depends on the order of the vertices that we choose. So this is one problem with greedy. So if you can actually figure out for the type of graph that we are using and try to come up with a particular ordering that suits for this, then greedy can improve, right? It may not always give the best, but it can still be much improvement over the arbitrary choice. So we need to be careful about choosing the order. Now, here is a couple of observations about greedy. Any order, whatever you choose, the greedy uses at most the maximum degree plus 1 colors. I mean, this should be very clear to you if you know how the algorithm works, right? So algorithm works by picking up a vertex, looking at the pre-colored neighbors, right, and then trying to give this color, this vertex a color which is not used in the neighborhood, right? So if you understand that, then you should be immediately clear that the greedy uses at most delta of g plus 1 colors. So again, I have written y so that you can try to frame it in a nice way on your own and then try to write it, this observation and with some reasoning. Now, again, the depends on the maximal number of colored neighbors a vertex has when it is being colored, right? This is that we have something observed, and it can depend, on the order, right? And that also we have seen, and this has some bearing with the previous observation that we. Now, using some we can come up with the following theorem, right? Nice theorem which gives an upper bound on the chromatic number. So, given any graph G, one can see, from the way the coloring works, right? That the chromatic number of G is upper bounded by maximum over all the minimum degrees of the induced subgraphs of G. So take the graph G and look at all possible induced subgraphs of G. Well, so what is an induced subgraph? Basically, it's a graph obtained by just vertex relation, right? So you can delete nothing, which means that the G itself is an induced graph. Then you can pick some set of vertices and delete them. What you get, the remaining graph is an induced subgraph, right? So if you have if you look at all possible induced subgraphs of the graph and look at the minimum degrees of this graph, okay, and take the maximum over all these minimum degrees. Now this plus 1 is an upper bound for the chromatic number. Okay, this is my claim. Okay, so I want you to think about this and come up with a reasoning why this is, and then try to write it down. In fact, I tell you that it directly comes from the observation that we had in the previous thing, with a small tweaking of understanding, like how do you see it, of looking at it. So I want you to think about this and come up with. And if you don't come up with this, you have to get back to me. Okay. If you don't come up with an answer to this, please come back to me in the next class or the class, the later one. I will explain it. Okay? It's very important you think about this. Okay. So in other words, what we are saying is that if you are talking about a minimal k+1 chromatic graph. A minimal graph. So the graph is k+1 chromatic, but any subgraph, right, is not k+1 chromatic. Must have a minimum degree at least k. This is another way to put the same thing that we mentioned before. Okay? So a minimal k+1 chromatic graph must have a minimum degree greater than or equal to k. If it is less than k, you can find a coloring with less than k+1 colors. So this is again something that you can try to show why. What we have understood from following the algorithm, how the algorithm works. Here is another observation. So given a graph G, we can look at the degrees of each of its vertices and put them in decreasing order. Okay, so collect the degrees of the vertices and put them in decreasing order. It's called a degree sequence of the graph. So degree sequence need not uniquely define the graph, of course, but you have the degree sequence which tells you something about now. So given such a degree sequence, right? So D1 is the degree, the largest degree appearing. Of course, it could be equal to D2, the second largest degree, etc. It could all be equal, but you have this inequality. Now you take this degree sequence, then the chromatic number of the graph is less than or equal to maximum over all I, right, between 1 and n, minimum of di plus 1, comma I. So choose the minimum of I and di plus 1, and then take the maximum among such pairs, right? No, not pairs, like among these values, right? The minimum of di plus 1 and I. So collect this, and so the ith vertex in this order, right? Its degree plus 1 and the value I itself. So collect this and then find the maximum among this ordering, and this will give you the chromatic number of G is less than or equal to this. So again, this comes from the way our coloring algorithm works. So all these can be somehow related to the greedy, okay? And we can use this, these facts to basically improve upon the choice of the vertices. So these things again you have to think about this, and try to formally try to come up with an argument on your own, and try to write it if possible. Otherwise, at least work out the details. And if you don't see how to do this, again get back to us. Discuss with your friends, and otherwise you get back to me. And once you have these observations, like that we have just come up with these 3 observations, we get an immediate corollary that the chromatic number is less than or equal to the order of G plus 1 minus chromatic number of G complement. Okay, so the complement of the graph, that also has some chromatic number, right? And basically, so this is saying in other words, it's saying that the chromatic number of a graph plus the chromatic number of its complement is upperbounded by the number of vertices plus 1. Right? This is the corollary. So again, take it as a homework, but it's a little bit tricky. So use the above result that we have just mentioned on the degree sequence, right? And then try to use this argument on both G and G bar, right? The complement. And then once you use these results from both G and G bar, and with some some manipulation, you should be able to come up with this identity. Of course, there are other ways to prove this, but this will be a nice way to think about this. Okay, so pick up these questions. Now, as we mentioned, given a graph G and maximum degree is delta, then the chromatic number is less than or equal to delta plus 1. Okay. So this is something that we have mentioned before. Now suppose the graph G that we are looking at is connected. If the graph is connected and the graph is not regular, Okay? So if the graph is connected and then not regular, then I claim that the maximum over all induced subgraphs, the minimum degree of h is actually less than or equal to delta minus 1. It's not going to be equal to delta. It's actually going to be less than or equal to delta minus 1. And can somebody tell me why? So here the assumption that the graph is connected is very important. So any idea? Anyone has any suggestions? Nishank? Anyone? Okay, so let me give you a hint. So since the graph is not regular, there is at least some vertex whose degree is less than or equal to delta minus 1, right? Some vertex whose degree is strictly less than delta. Now, we have mentioned some point of time. Uh, I hope so, at least given us as an exercise or something, that if you have a okay, or at least think about this. Okay, if I have not mentioned this before, I am not sure now. So if you have a connected graph and then you pick any vertex, okay, you can find an ordering or okay, you already know. Okay, in fact it is not required. You can start from any vertex, right? We have done this in another way. If you start from any vertex, you can basically use one of the tree growing algorithms to find a spanning tree from this vertex, right? So since the graph is connected, you will find a spanning tree. Now, if you have a spanning tree, then starting from the vertex that is a root that we have picked up, right? So we start with a vertex whose degree is strictly less than delta. Then you have the spanning tree. Now because and you can actually grow the spanning tree so that so we have learned in Prim's algorithm, right, that we can grow the spanning tree where the every time we are growing it is going to be connected, right? So we are basically growing it one by one, right, adding new neighbors. So if I go in this particular order, you will see that so this last vertex, right, the first vertex that we choose in if you reverse it, has a neighbor to the previous vertices, right? And since I have a neighbor to the previous vertices, right, the I mean a neighbor forward, right, not the previous, in the forward, you always have the for the subgraph that we are going to look at, you are always going to have. So if I remove this vertex, you are going to have basically a graph where at least one of the vertices cannot be of maximum degree, because it has some neighbor which lose one of its neighbors. So therefore, using this the spanning tree algorithm, we can see that you will have an ordering to remove the vertices where I always keep on removing a vertex of degree less than delta. And therefore, each of the subgraphs must have also, also maximum degree, the minimum degree less than or equal to delta minus 1. So that is the idea. Okay. So this is going to give you this bound for the chromatic number, that the chromatic number is less than or equal to delta because the maximum or the minimum degrees of induced subgraph is less than or equal to delta minus 1. Okay. Now the question is that what if the graph is regular of degree delta, right? So if the graph is regular, right, if it is not regular, we can do this, right? Because all the vertices have degree equal to delta, then we cannot do this because we cannot pick the graph itself has a is a induced subgraph, and therefore the maximum is actually equal to delta, right? So therefore we don't know what will happen in this case. So if the graph is regular of degree delta, every vertex has degree delta, we don't know. So this question, right? So we know that the chromatic number is upper bounded by the maximum degree plus 1, but now we are asking, is it less than or equal to delta, right? Can it be less than or equal to delta? So theorem by Brook answers this. So what we know is that if the graph that we are looking at, the regular graph we are going to look at, is the odd cycle, then the odd cycle requires 3 collects, right? And the cycle has degree 2, it's 2 regular, but it requires delta plus 1 collects, which is 2 plus 1 equal to 3. So if the graph is an odd cycle, we know that we need delta plus 1 collects. We cannot do with that delta. What if the graph is the complete graph? Right? So if the graph is complete, we know that all the vertices must get different colors. So if if you look at the complete graph on n vertices, then it's regular with degree n minus 1, because every vertex is connected to all the remaining n minus 1 vertices. And it's regular with degree n minus 1, and it requires n colors, which is delta plus 1 colors. So if the graph is regular, for the case when the graph is an odd cycle and when the graph is a complete graph, in both cases we require delta plus 1. But what about the other regular graphs? We can have other regular graphs, right? Which might require delta plus 1 colors. We don't know, right? So Brooks theorem in fact says that if the graph is neither a complete graph nor an odd cycle, then the chromatic number is always less than or equal to maximum degree. I'm going to give you 2 different proofs. Okay? So the first proof, I'm going to essentially give you several why questions. Okay? So I will give you the statements. You try to prove it. Okay? And then the second one I will make it slightly more complete. The second proof. But of course, it would actually help if you think about these questions before you actually see the proof. But I don't know how to do that because I will be covering both in the same class, I believe. But no, today I will only cover the first proof, I believe, the first proof of Brooks theorem. So this is the following. First, we observe that we can always assume without loss of generality the graph that we are going to look at is a 2 connected graph. Okay, so that there is no cut vertex. So I mean, of course, we can assume that it is not it is connected. That is first immediate observation, and the second immediate observation that we can assume that it is 2 connected and there is no cut vertex. So I want you to think about why we can assume that the graph is 2 connected. Okay, so this is the first thing that you want to prove. So what I would like you to do is to think about this today itself, right? These 4 questions today itself, because tomorrow when I start the second proof, if you have not figured out this, let me know, and then I will try to explain why. Okay, so we can assume without loss of generality that the graph is 2 connected. Then, secondly, we can assume that the graph is regular in degree delta. Of course, we mentioned why. Just try to write it down here again. That we can assume the graph is regular in degree delta. Then, third point is that it suffices to show that the graph has a pair of vertices, let's say A and B, such that the distance between A and B is actually equal to 2, right? Which means that they both A and B has a common neighbor, right? That's why, and there is no edge AB, right? So A and B there is no edge, and AB has a common neighbor, let's say X or something, right? And the graph G minus AB is a connected graph. So if I have such a pair of vertices that the vertices have a common neighbor which are not adjacent, these two are not adjacent, that has a common neighbor, and after removing these two, the graph is a connected graph. Okay, again, try to see what we did with the connectedness property in the previous argument that we have, right? So try to come up with a use of what we have learned, like the Prim's algorithm, or like the tree growing algorithms, and try to connect it with this, and then try to show that if I have a pair of non-adjacent vertices which has a common neighbor, that is and such that removing these two vertices will result in a connected graph, it will solve our problem, that we can find a delta column. Okay. And finally, if we have we have a regular graph that is too connected and it's not complete, right? Then suppose for some vertex A in the graph V, in the graph G, suppose G minus this vertex, G minus A is too connected. Okay. So after removing some vertex in the graph, I can remove and keep the graph still being too connected. Then we can always find a pair of vertices A and B which are at distance 2, and removing A and B will not disconnect the graph. Okay, so this is another claim. Right? So I have the graph G. If I remove some vertex A, right, then the remaining graph is still two connected graph, right? Something like this. So I have this A, and removing this, I will still get a two connected graph. Then I can find a pair of non-adjacent vertices whose removal will not disconnect the graph. Okay, so this is another claim. Again, think about this. And once you have all this thing, okay, we can assume that, okay, suppose it is not the case, right? So G minus some vertex, let's say X, is, you cannot find such a vertex, so therefore G minus X is separable, which means that it has a cut vertex, right? So after removing one vertex, you end up in a graph which has a cut vertex, right? Then you can find, such a pair from any two distinct, okay, I think I have missed something here, distinct n blocks of G minus X. So what are n blocks? Okay, so n blocks are basically, blocks which are incident to only one cut vertex. So we already talked about blocks of a graph. Blocks are the graphs which has no cut vertices, right? So if you have some graph which has several cut vertices, right, then if you look at the the structure of the graph, you will see that there are several what is called blocks, right? This we saw in some of the classes. The blocks, and the blocks are connected by cut vertices, right? Now, if a block has only one cut vertex, incident to it, of the graph which is incident to it, then that is called an n block. Okay? And one can show that if a graph has a cut vertex, it has at least two n blocks. So then if you pick any two distinct n blocks of G minus this vertex X, you can show that you will find the pair of AB, the pair of non-adjacent vertices with a common neighbor that we are looking at. Okay? So again, try to show that this is indeed the case. And if you can actually come up with this for properties, then you can use this to color all such graphs, which is different from, of course, odd cycles and complete graphs, with at most delta colors. So this argument you can give by finding such a pair and using it to color it, using the observation that we have here, right? It suffices. So if you prove this, then once you show that such a pair exists, you are done. Okay. So this actually winds up the proof of the Brooks theorem. Of course, once you fill up the gaps with the proofs. So go back today, and today itself think about these questions. Very important, right? Think about these questions and try to answer these why questions, and then try to come up with a complete proof of Brooks theorem. So once you think about this, tomorrow when the class starts, let me know if you have any doubts, and I will clear it up. So that is the thing. Then I will give you the second proof of Brooks theorem. So, but I think our time for today is already almost finished. So I will probably start with the second proof tomorrow. But maybe something you can think about. Okay. So here is another thing that I want you to think about. Suppose and this will help in coming up with a proof, a different proof of root theorem, and in many other cases. Okay, so this is what I want you to think about. That suppose I give you let's say a graph and a proper coloring of this graph. So I give you a graph and consider any proper coloring of this graph. Now, if you take any proper coloring of this graph, and then let us say that I pick up okay, so take any proper coloring of this graph and pick up any color class, any two color classes. Look at the subgraph induced by this this two color classes. This is vertices of, so each color class is an independent set. Therefore, if you take any two color classes, then it will form a bipartite subgraph. Right? If you take any k color classes, then it will form a subgraph which is k-partite, which means that there will be k independent sets in that. Right? And then so take, for the time being, let us just think about just two. Right? Take two color classes and look at the induced subgraph of these two. Let us say that the pink and the yellow, right? So pink and yellow, look at the subgraph induced by this. So which means that you will have this edges here, right? This one, right? And this one, right? Similarly, this one. So this is the subgraph that we have, right? Pink and yellow. Now, if you take such a subgraph and just take one of the components in this subgraph, right? So take some component of this subgraph. And then I just switch the colors pink and yellow here, right? So I will make all the pink vertices in this subgraph as yellow and all the yellow vertices as pink, right? So I will make this as yellow and this as pink instead. Now, if I do this, I still get a proper coloring of the graph without increasing the number of colors. I mean, this is kind of obvious, but I want you to convince yourself that this is indeed the case. And you can in fact do it for any set of colors. Okay? So think about this also. We will use it in the next day's proof. Okay, I think we have done enough for today, and we'll continue in the next class. So any questions, please feel free to ask.